Thank you, Antonio. Let me introduce our last speaker for this morning, Peter Hunter. Peter Hunter is a professor of engineering science. He's director of the Bioengineering Institute at the University of Auckland in New Zealand and co-director of computational physiology at Oxford University. He completed a Master of Engineering degree on solving the equations of arterial blood flow and a PhD in physiology on finite element modeling on ventricular mechanics. His major research interest has been the interrelated electrical, mechanical, and biochemical functions of the heart. Peter has been helping to lead the international Physium project, which aims to develop model and data encoding standards and to use computational methods for understanding the integrated physiological function of the body in terms of structure and function of tissues, cells, and proteins. Peter is a fellow of the Royal Society in the UK and in New Zealand, and a member of the Order of Merit in New Zealand.
Thank you very, very much, Nicola, and also it's wonderful to discover it's a great honour to be here, but also to discover the link with Claude Bernard, who I think is really the father of the application of physics to understanding medicine. So I'm going to do this talk in two parts. I want to mainly talk about developing the frameworks that the Physiome project and the UK and the European Virtual Physiological Human has been developing for trying to make sure that models of biological function, multi-scale models, are built with standards and able to be reused and in a modular fashion. But to motivate why we think this is important, before I talk about those frameworks, I just want to give some examples of particular cases where these frameworks have been used to link clinical applications of modelling down to molecular events. So all of these examples are attempting to link the molecular behaviour to the physics of the whole organ, and to do it with clinical applications in mind. These particular examples come from the Auckland Bioengineering Institute, but they're all in collaboration with many other people around the world, and they only represent a small fraction of all the modelling of this type of computational physiology modelling that's going on around the world, but these are the ones I'm most familiar with. So first of all, the heart work is where we've had the longest track record of developing these frameworks, and it's led by a number of people in playing various roles, Bruce particularly in the experimental work, Marty in the development of the biomechanics models, Alistair for the clinical applications of the Cardiac Atlas project, and so on. Nick Smith is another one who's been very involved, particularly in the coronary side. So the framework looks like this. The idea is that we want to be able to use physics to understand function at the whole organ level in a way that's relevant to using images from the clinic, but build our understanding of the physics here based on continuum models that have a lot of knowledge of tissue microstructure. So we build a lot of instrumentation to measure structure that can then be captured by those models and used in the interpretation as part of the solution of the physics. And of course, linking to cellular processes. So over the years, we've developed many models and worked in collaboration with people around the world who've developed models of cellular processes, and a lot of the frameworks that we're developing now are really to cope with the complexity of the biology that occurs in cells, and in some cases requiring three-dimensional models, and in some cases linking down to protein sequence or amino acid sequence and genome information. So here's the overall scheme, and although described here for the heart, it's equally applicable to all your other organ systems that I'll talk about. Typically, you try and merge the physics of a number of different processes. It can be mechanics, blood flow, soft tissue mechanics, blood flow, neural control, and so on, electrical processes for activation. In some cases, these models need to be linked to how current flows out of the heart onto the torso in order to be able to interpret clinical measurements of potential on the skin. They're all continuum models, but they all rely on this notion that you really want to delve into the underlying structure of the tissue and also delve into the cellular processes that are driving the physics up here. And the classic example of this are the Hodgkin-Huxley equations for ion channel electrophysiology, which one of our collaborators, Dennis Noble, has been leading the way in terms of the interpretation of ion channel electrophysiology into whole heart work. And in some cases, these go beyond the standard Hodgkin-Huxley into Markov. In some cases, it goes to molecular modelling, and we try and understand the parameters in these models in terms of molecular behaviour, and in some cases, 3D modelling. In all cases, imaging is crucial at all scales, from the whole organ, typically with the MRI or ultrasound clinically. Increasingly, we're using micro-CT with new generation micro-CT that gives comparable resolution to confocal, and all the way down, depending on the model being developed at the different scales, electron tomography being used for understanding cellular structure. And then also, in all cases, the other key component is the physics. And here, the really important point is that we're building on 150 years of effort by mathematical physicists to capture the laws of nature in a form that can be solved on a computer relatively easily these days. So these are the beautiful equations that really underpin all the physics that we then do on this complex anatomy. And in some cases, that needs to go down to, to be refined with particular assumptions for different scales. But I think the most important point is that in all of these equations, there's little black boxes. There's little descriptions of parameters. It might be a diffusion tensor, or a current source, or a viscosity term, or a stress-strain relation, and so on. These are terms that are typically measured in an engineering sense. You do experiments to measure these parameters, but really these are the points where all the biology comes in, because you want to understand how the biological structure and function at all these scales gives rise to the coefficients that are used in the equations of physics at these scales. So a lot of the work is really trying to probe into what is behind these little black boxes, and make sure that probing is dealing with molecular mechanisms as well as details of structure that exist at all scales. So one example, for example, in the cardiac case, where we want to be able to measure the biomechanics of soft tissues experimentally, and then measure the structure and understand what we can measure with a sample of tissue that's being held inside this set of pullers that have 2-axis force transducers on each tethering point, and then we can image using speckle techniques, image the displacement fields, and then understand the relationship between the boundary conditions and the deformation. And then using a model of that tissue, we can extract the spatially varying material parameters that can then go into a description of the constitutive properties of that tissue for use in the whole organ models. In the case of active properties, we build equipment that is able to measure the tension, the action potentials, calcium transients, heat production, and so on, of little trabecular strips, in order to be able to derive the equations that then plug into the whole organ models. And I think another important point about this type of modelling is that it's a way of fusing data from multiple sources. So in some cases it's molecular data, structural data, as I've mentioned. In other cases, clinical data from MRI or ultrasound or CT. And Alistair Young, as I mentioned, is leading the way at Auckland in terms of linking the clinical imaging work on the heart into the Cardiac Atlas project. but also it's a way of bringing physiological data into the same frameworks. So the models become the way of merging all of these scales and the spatial variation, in this case of a particular current, calcium current, that varies spatially around the heart and needs to be part of the description of the underlying physiology of this organ model. Another example is the lungs, led by Merin Tawhai in Auckland with a team of people, and very similar approaches, building models of the detailed structure of the airways, the vasculature, gas exchange at the alveolar level, and then using these models to, in clinical settings, to be able to particularly differentiate different patient groups with, and this is a normal lung here and looking at perfusion ventilation ratios, but in cases where patients have embolisms, the structure of those embolisms can be imaged, put into models, and then that can help in the diagnosis of treatment strategies for individual patients. Another example is the musculoskeletal, and here led by Tor Bézier, and the idea now is to build models of all the muscles and bones in the body, tendons, ligaments, and be able to create libraries where we can pull these components into composite models to look at the mechanics of particular joints. So if we're interested in studying, say, the detailed stress distribution through the knee joint, we can use these finite element models of mechanics occurring at this large scale, but then link this to down where we know the loads being transmitted into the various structures here. Then we can apply those loads in the lab to look at how the tissue responds to abnormal loads in terms of gene expression, and look at use microstructural models to understand how these loads get transmitted to signaling systems, for example, that occur at the cellular level, and then feed that back up to the whole organ level. So always there's that attempt to link what we can measure and use physics-based models to interpret, but always to then push down to understand the molecular mechanisms behind particularly disease processes. Here's another one with the GI tract, the gastrointestinal system, led by Liu Cheng, and here the idea is to build models of the stomach and intestines, looking in this case at slow wave propagation, because there's a number of diseases of the stomach associated with dysfunction, associated with particularly the interstitial cells of Cajal. So we model the cellular behaviour, do validation with building instrumentation to be able to make sure that the models are getting it right in terms of this whole organ behaviour. And then finally, my last example, very briefly, is work, more recent work from Mark Sagar in the lab at Auckland, working on building models of the face with very detailed descriptions of all the tissue types underpinning facial structure, and then being able to drive these models from the neural input into the individual muscle components inside the face. And what Mark is doing now is to try and close the loop, to be able to use sensory information with models of various structures in the brain to be able to then provide the appropriate outputs to drive the facial animation and close the loop on interaction between the model and someone communicating with it. So those are the particular examples that really demonstrate the need for the fact that it's multi-physics. There's often lots of physical laws required to understand the function of an organ. We have to be able to demonstrate reproducibility. If people other than those who develop the model are going to use it and build on it, we need to have modular approaches, again, because any one group, for their work to be able to be incorporated into the larger scheme of things, we've got to understand how to build modules and incorporate models that import modular structures. And it's essential that we have data and modelling standards to make sure that we are doing reproducible science as part of this whole effort. So the history of the Physiome project is that It was started by the International Union of Physiological Sciences in 1997. They asked me to set up a committee that then began the development of, we developed the markup languages to provide the standards behind the modelling. At the same time, the systems biology community began the development of SPML, which is another XML-based markup language. And then the US contributed through the IMAG program with a number of US institutions. And then the European Union, or European Commission rather, began with the STEP project, and then leading to a number of European projects called under the banner VPH, Virtual Physiological Human. And then more recently, another part of the European Commission co-funding with pharmaceutical companies to bring these standards into the world of pharmacokinetics, pharmacodynamics for drug discovery. And then another example of a European project that's contributed greatly is the German Liver Network, funded by the German government, BMBF, which is also using similar multi-scale and building on these processes. And we've established a virtual institute, the VPH Institute, which is now helping to keep the momentum going in Europe particularly, but for the whole world really, in terms of the use of these frameworks. So what a lot of the early work did was to develop standards. I mean, DICOM obviously had been around for quite a while, but develop other standards for encoding data and building APIs and web services to be able to, in the appropriate annotation, to be able to access data sets, and then standards for modelling, SPML, CellML, FieldML, associated model repositories with the metadata using the bio-ontologies like the gene ontology and the foundation model of anatomy and so on, modular approaches, and building APIs and web services to make the model repositories accessible with automated querying. And then finally the development of another markup language, ZML, which deals with the simulation standard itself, the way you do the simulation. And then a range of open source, freely available open source software platforms that make use of these standards and can pull models in from these databases. And these standards now are being used by a number of journals. For example, the Biophysical Journal strongly encourages people to, authors who are submitting models, to make use of these standards when they submit their models, just in order that referees can run the models, but also that readers, when they're published, can get hold of these models in standardized forms and use the available software to solve them, to run them. So here's our challenge. We've got to go from molecular biology. We've got 50 years of developing very detailed parts list for the genome and the proteome and metabolome and so on. We know there's around 300 cell types that use all of these processes in variable ways. And we know that each tissue type in the body makes use of a relatively small number of cell types to achieve the function of the tissue. And at this point, the relationship between structure and function is crucial. So in each one of these, like the nephron and the kidney, it's the structural organization of a relatively small number of cell types into a three-dimensional structure that determines the function of that particular module that then scales up to become a whole kidney. And that scale-up process is often just a case of whatever you've built here for dealing with filtration is then multiplied 1 million times for a kidney in a human, or multiplied a much larger number of times for a kidney in an elephant. So a mouse and an elephant have very much the same structures at this scale and down. They just have more of them. And so it's the circulation system that's branching more to be able to cope with the filtration load of a large animal versus a small animal. And so a lot of the multi-scale structures that we're developing for the Physiome project need to be able to take the models developed at this scale associated with cell types, tissue types, plugged into the physics that's going on at the organ scale. Generally, we want to make, wherever possible, make these models biophysically based, because then you bring in a whole lot of a priori information. You've got to satisfy the laws of physics, use standards to make sure things are reproducible, and wherever possible, we need to be able to automatically assemble these models from these databases of components. And another crucial part of this is the model reduction process. We've got to be able to reduce complexity when you're using complex models as part of larger organ scale models in order to keep the computation times reasonable. And this is an area that needs a lot more work, I think, but is absolutely crucial for the use of these frameworks in clinical settings. And as always in science, often the starting point is the development of new instrumentation. Science often depends on people inventing new ways of doing measurements and then using models to interpret those measurements as part of the acquisition of new knowledge. So here's all 12 organ systems in the body, and there are now physiome projects around all 12 organ systems. And here's the website for the CellML standard for the cell modelling, which has got a large number of, there's about 500 or 600 models covering all aspects of biology, many of them curated and available for download in open source software. The other crucial part of this is that the framework allows, because of its modular construction, you can import models to create a more complex one by importing submodels. And so, for example, you could be creating a PK/PD model for the drug discovery using models of individual components that are then imported. So it's not just at the cell level. It could be, if it's lump parameter modelling of all of these, they can be imported into a higher level modelling. And in the case of the cardiac myocytes, we're building models that start with the electrophysiology and calcium transport in cells, pH control, bicarbonate control, and then force production, and then all the signalling that builds on top of that. So beta-adrenergic signalling leading to, in some cases, regulation of transcription factors and gene regulation. But then all the other signalling processes that end up phosphorylating proteins that are involved in the control of electromechanics in the heart. And so all of these individual modules can be built and tested and validated independently, but then the frameworks allow these to be pulled together into composite models that might be used as part of a whole organ model. The same with metabolism, so we have modules representing each of the enzymes, and this has now been done for the liver cell and cardiac myocytes, that can then be imported depending on the questions being asked of them of a more composite metabolic model. Alan Garney, who's working in INRIA, in fact, is developing open source software called OpenCore, available here, which is the main simulation software now for OpenCell, and allows you to import models directly in CellML and run them or edit them and interrogate the outputs and deal with the mathematics, interrogate the mathematics of the models. So I wanted to finish by talking about some more recent work that I've been doing with Bernard de Bono. He's got a joint appointment between UCL and Auckland. And this is really trying to now map these modelling frameworks onto medical informatics. So we've published several papers in the last few years that are beginning to think through the process of how we link a lot of these modelling frameworks into medical applications through use of medical informatics. So there's a scheme here that Bernard invented, which I think is a very powerful way of looking at all of physiology. You imagine a 2D map, 6x4 segment shown here, where the entire vasculature is built into here, the GI system here, which is all of this, the skin, this is all the muscles and etc. And here's the neural system, the lungs. So everything on the outside represents epithelial contact with the outside world through epithelial cells. So for example, the lungs, the epithelial tissue is invaginating, of course, all the way through the lungs, but is connected to the outside world as part of the airway structure. All of the skin appears here. All of the lining of all of the digestive system appears here, and so on. And then we can, because of all of this is then mapped onto the foundation model of anatomy, which is a terminology with tens of thousands of terms for all of the anatomical components in mammalian bodies. And so what we can do is zoom in to any part of that 6x4 template and interrogate, and automatically you'll have all the terms appropriate from the FMA displayed. And so this is dynamic. You can zoom in and interrogate any part of the body. But then we can begin to map structures onto it. So, for example, we solve one-dimensional Navier-Stokes equations with elastic blood vessels and can compute pressures and flows or advection diffusion for drugs around the body. But then we can map how these structures here map into the tissues at all points throughout the body by projecting with the appropriate terms through the FMA, through the foundation model of anatomy, onto all of the tissue structures. And then we can delve into the response at any particular tissue to changes that are going on associated with the organ, the whole circulation system. Similarly, for neural networks, we can map them into structures in this two-dimensional map. And then finally, in order to be able to understand how structure function works at the tissue level within each of these FMA tissues, we want to be able to define what we call a primary functional tissue unit, or PFTU, which is a small volume where any communication is happening by diffusion, not advection. And so here we're looking at ways of automating the processing of histology images to be able to find these primary functional tissue units and build them up and annotate them automatically so that we can begin to locate all the cell types that exist inside each of these primary functional tissue units in order to then build up to the next structure, which we call secondary FTUs, and then link those on a high data throughput basis based on lots and lots of measurements through to the modelling of the physics at the larger scales. So this is just beginning, but I think is going to be a great way of being able to tap into a huge amount of imaging resource and link it to the modelling, multi-scale modelling frameworks that I've been talking about. So part of that process is going through the whole of the body, of mammalian bodies, identifying for each of the 12 organ systems, some of them shown here, identifying what all the tissue types are, what all the cell types that exist inside each tissue type, and what the primary function of each of those cell types are. So we've now done this. This is a table that's available through a recent, for the whole body, through a recent J. Physiol publication. It's really just the beginning of this process, but it's an attempt to try and take a very holistic view of what all the structures are at each scale and try and be able to link high throughput molecular biology data through to the physics-based and image-based modelling at the clinical level. So with that, I'll just thank lots of people who are involved in this work. These are people leading work in Auckland that I've talked about, and acknowledging that always with the development of these frameworks, a lot of the effort goes into not just building models, but building the instrumentation to acquire the data or to validate the models. So we have a large team of instrumentation engineers who build the equipment that's needed to be able to make sure that this modelling is relevant to, that we're dealing with reality and they're validated models, and look for clinical applications. And then the team of people that are involved in the development of the standards, CellML and FieldML, and of course lots and lots of students and postdocs who've contributed to the work. And the funding for this comes from a number of New Zealand sources, but also through the European Union from Framework 7 projects like UHeart that Nicola's also involved in, and various NIH projects, including the Cardiac Atlas project, which is funded by NIH. and here's the website for the VPH Institute, and here's the reason why you should come down and visit us in Auckland. So, thanks very much.